So, hello everyone, welcome back to the course on architecture and design of ICs. So, in the last class we have seen Booth's algorithm, then sign extension, that means template method for reduction of the sign extension. Okay. So, after that what we have seen, again we have seen that means block diagram representation of Booth's multiplier, that we have seen. Okay. Now, we will see, and whenever we are that means after Booth's multiplication or after using of this Booth's algorithm, we are getting the number that basically we use Booth's algorithm to reduce the number of partial products. So, once we generate the partial products, then again I have to add those partial products to get the final result. So, those whenever we are doing those partial products adding unit, so at that time I can use this tree reduction method. Okay. So, apart from that, instead of Booth's multiplication, there are tree multiplication too, like this Wallace tree multiplication and other tree multiplications are there. So, there also we are doing this that means this reduction in the depth of the adder in chain operation, okay, using this binary tree. So, in today's class we will see those tree multiplication or how we can reduce the corresponding number of delays or the number of full adders, in what aspects I can basically do the reduction, that we will see in today's class. Okay. So, let us start with this tree multiplication. So, in this the first multiplier architecture, this is nothing but the serial one. Okay. So, that means the once it is coming using one adder only, this will be run in repeatedly and I will get the corresponding results. Okay. And if I that means use all the multiples together using carry save adder tree, and finally at the very last stage I need one full, that means carry propagate adder. So, and then I can get the results which is basically the full tree. This is one method, and then there is another method where I can consider partial tree, that means the whole tree instead of this whole tree, if I consider only partial tree and I use or I calculate some of the, that means carry those using carry save adder, and I use very few parts of these partial products, and then finally I add those in a carry propagate adder. So, at that time also I can do that. So, that means the tree multiplier, that means this multiplier are categorized into three different architecture. So, one is that where I am considering all the multiples, one is that where I am considering only single multiples, and one architecture is there where I am considering the partial multiples. Okay. So, then if you use these particular things, so at that time area wise there is savings, but speed wise this is poor. At this case area wise this is poor, but speed wise this will be much more better. Speed means computation time. I am not telling that speed means the frequency of operating frequency of that particular circuit, but the corresponding that computation time for the multiplication, that is reduced in this particular case in case of instead of this. But in case of, that means some part in serial, that means in this middle case what we are doing, we are not doing here what in the first architecture what we are doing, we are considering single multiples and then we are serially doing. And in the last architecture what we are doing, we are considering all the multiples and then parallelly we are doing. But in this mixed culture, this mixed architecture what we are doing, we are considering serial, some of the things in serial, and those serials are basically running in parallel. Okay. So, that means the mixture of this serial and parallel together gives me the benefit of area as well as the speed both. Okay. So, that is why we that means this mixed architecture for serial and parallel, okay, they are basically optimize in terms of power and area in with respect power and speed, or that means in terms of computation time for in compared to both of these circuits. Okay. So, if I consider this full tree architecture, so at that time in full tree, that means this tree multiplier architecture, it has three parts. One part is this multiple forming circuit. So, multiple forming circuit is nothing but the generation of the partial products. So, that means this also can be named as this partial product generation unit. Okay. So, those are nothing but the AND operation, because each bit is ANDed with that means each bit of the multiplier that is ANDed with each bit of the multiplicand. So, that means that is why this is, that means that those are the multiples. So, that is why this particular circuit is named as multiple forming circuit. Then the next part is this partial products reduction tree. So, after generating the partial products, what I have to do? I have to basically add those partial products. So, while we will add those, at that time I can use this binary tree or this tree that means addition operation to reduce the corresponding delay for that. Okay. And the third one is that then redundant to binary converter. So, once I generate this, then this is for that means the final output generation unit. Okay. So, this part is basically the main part where I am doing this partial product reduction tree. So, this basically, that means this is the major research area or the focus area where people have tried so many, that means way out to find out, that is to find so many way out to reduce the tree in a such a way, so that the multiplier becomes high performance. Okay. So, that means these are the things which are related to this multiple that means this tree adder components or this tree adder multiplier architecture. I have already discussed that multiple forming is nothing but the combinations or this, that means it uses those AND gates for bitwise multiplication. Okay. Then partial products tree, that is basically uses the carry shaped adder tree, that is the examples are like Wallace tree and Dada tree, that we will see, and produces a redundant results, that is carry and save outputs, and some lower bits produced directly. So, that means that some of the things, some of the bits are generated and the lower bits are directly it comes as the output. So, after getting that means after adding those, finally it will be of 2, that means 2 number will be there. So, while I will get only 2 numbers, so at that time I need to use one first adder, either you can use carry propagate adder or conditional sum adder for those kind of addition. So, at that time this basically comes to as the part of this redundant to binary converter. So, if we chose one example of that, so at that time it will be much more clear to you. If I have to multiply 5 bit, so I have to generate 5 partial product set. Okay. So, each set containing 5 these numbers. So, that means this 5 post partial products and each requires 5 AND gate to produce this each of these multiples. So, total I require 25 AND gates in multiple forming circuit. This is nothing but the partial product generation unit. So, after that what I said that I can use different tree reduction method for this partial tree generation, that means for addition operation. So, in Wallace tree, what we do in Wallace tree, as soon as possible these multiples are, I will get those multiples, I will try to add this. Okay. So, and while I will add, after that at the very last stage I will get only 2 input of that. Okay. So, and finally using a carry propagate adder at this level I will get the final results. So, here you see I need to add for 4 cross 4, that means this case I have to use this 2 carry save level, which is one here and 2 5 full adder cell as well as 3 half adder cell and 4 bit carry propagate adder. At this is the carry propagate adder and these are the, that means half adder and full adder cell. Okay. So, total 18 number. So, 5 full adder, among them 5 full adder and 3 half adder. If I use this data tree method, in data tree method, that is as late as possible you have to add. In Wallace tree as soon as possible we are adding, but in data tree method as late as possible we are adding. Okay. So, there are also 2 carry save levels. Along with that I have to use 6 full adder, 2 half adder and 6 bit carry propagate adder. In the previous case how many I am using? 4 bit carry propagate adder and 8 adder cell, among that means in between 5 full adder, 3 half adder, but here 6 adder cell, among them full that means 4 full adder cell, 2 half adder and instead of 4 bit in case of Wallace tree 6 bit carry propagate adder I have to use in data tree method. Okay. So, then if I, that means take one example of that. So, at that time you can see, that means what is this number 1 2 3 4, that means 3 2 1, what is these numbers? Okay. These numbers are basically coming, for, because what we have considered? We have considered this 4 cross 4 multiplier, right. So, 4 cross 4 multiplier it gives me what? At the very first I will get P1, P2, P3, P4, sorry P4, right. Then what I will get? I will get, sorry, P5, P6, P7, P8, something like this, then P9, P10, P11, P12, okay. Then P13, this is 13, P14, P15 and P16, okay. So, if I just want to add at this particular position how many numbers? 1. So, this 1 corresponds to this. Then at this position how many numbers? So, 2. So, this number corresponds to this. Then at this position how many? 3. So, this 3 corresponds to this. Then at this how many? 4. So, 4 corresponds to this. Then this is 3, 3 over here, 2, 2 over here and 1, 1 over here. Okay. So, that is why these numbers are basically how many numbers I have to add at this particular position, that indicates by these numbers. Okay. So, now if I, that means now whenever I will consider at the time for these 2 numbers if I have to add. So, at that time I need one half adder over here, for 3 I need one full adder, for 4 1 I need one full adder, for 3 I need one full adder. Okay. So, after that this will produce the carry over at this 4th stage. So, this will that means forward the carry to this stage and this will forward the carry to this stage. Okay. So, after that, that means at this stage, so this carry will be forwarded over here. So, 3 I have already consumed, but it produced 1 and the carry produced from here, that means from this particular level. So, that will become 2 over here. So, 3 I have consumed, 1 I have left. Okay. So, 1 has been generated from this, that is another 1 and the carry from here. So, that number now it will become 3. So, 3 I have already consumed and produced 1. So, 1 over here and 1 carry from this particular stage. So, this will be 2. So, here there was 2, but 1 carry from this particular level. So, this will become 3 now. Okay. So, then after that I have to use one half adder for this 2, full adder for this 2, half adder for full adder for this 3, 2 for this half adder, 3 for full adder. Okay. So, once again I consume, that means this half adder for this. So, this will produce 1, this 3, that 1 and carry from this. So, it requires 2. So, then again 2 it is consumed, produce 1, 1 from this particular carry. So, that is 2, 3 consumed by full adder, produce 1 output. So, carry from this particular level. So, that becomes 2. So, initially there was 1 and the carry from this particular level, that will affect to the next stage. So, that will become 2. So, that means 1 1 1 that directly come to the products, but for these 2 I need one 4-bit carry propagate adder. Okay. So, this is the Wallace tree method. What happens in data tree method? Okay. So, the same numbers I will get, but here you see I am choosing at the middle where I am getting this 4 and 3. Okay. So, I have started from the maximum position, addition at the where I am getting the numbers are in maximum. Okay. So, full adder for this 4 and full adder for this 4 at the very first level. Then in the next, so 2 is already there, 3 is already there. Then here I have consumed 3, there is already 1. So, and it produce 1. So, that means sum along with the another input, that is gives me 2. For this it produce 1, the carry from this particular level. So, 2 and the carry that means the generated from this stage, that will come over here. So, that becomes now 2 becomes 3. So, in the next level what I will do, I will use for 3 I will use full adder, for these 2 I will use one half adder, these 2 I will use one half adder, these 3 I will use full adder. So, at this particular stage, so 2 is 2, 3 will produce only 1. Okay. So, then 2 produce 1 and the carry from this particular level. So, that will produce 2. So, 2 produce 1, carry from the other level 2, sorry. Then 3 consumed and produce 1, carry from the previous level. So, that will produce 2. So, 1 here, the carry propagated from, that means the previous stage, that becomes 2. So, now this 2, 2, 2, 2, 1 and 2, that I need to use, and that will be using 6-bit carry propagator. Now, I will get the corresponding results. Okay. So, here apart from that, another thing also here you can do. So, at this particular level, whenever I am considering, so I can use one half adder over here. So, if I use half adder, so at that time if I use one half adder over here, so at that time what will become? It will become 1, this will become 2 at that case. So, that means these 2 will directly come and I can use this. At that time what I require? I will require 5-bit adder for doing this, but at what cost? I have increased by the hardware by one half. That means, here what I am doing? I am putting one extra hardware, that means half adder, but I can reduce the adder tree by this 6-bit to 5-bit. Okay, that also I can do. So, this is the basic difference between Wallace tree method and data tree method. Okay. So, this is the, that means corresponding block diagram level representation or block diagram level this implementation technique of 7x7 multiplier, this using this tree reduction method. Okay. So, whether that is Wallace tree or by other data tree method. So, this is the at the very final level I have to use this carry propagate adder. Okay. to find out the final results. And this is nothing but the whatever that in the previous example whatever we have seen, this is nothing but the block level representation of that. Okay. So, then in that means tree reduction method, what I that means say that what I find out that the corresponding that methods are very much irregular in the sense. So, somewhere I am using full adder, then I am half adder, there is the structure is not that much regular. Okay. So, that is why this VLSI implementation of this particular this Wallace tree or data tree that can create some of the issues. Okay. So, to remove or to get out of those problems, okay, what we can use? We can use this 11:2 compressor or we can use this 4:2 compressor. So, these particular methods basically are very much useful as the structure is regular. So, this is that means for the VLSI implementation of those multipliers architecture that gives some of the mileage or gives some of the advantage to the circuit realization. Okay. So, in 11:2 compressor the method basically applies in the vertical direction, okay, and it creates one column replicate side by side and a carry created at level I enters into level I plus 1. The three methods are very much balanced, it consumes 11 inputs together and produce 2 outputs finally. So, that means the thing is that means suppose in one case if I am having the partial products up to P 11, that means the numbers are something like this, I need to add for this one particular position. So, at that time I can use this 11:2 compressor to add these terms. Okay. So, the same thing if I use 4:2 binary, so at that time this will be only P1 to P4. That will also produce 2 binary, one that means sorry 2 output, one is sum, another one is carry. So, that means whatever is the corresponding that means the numbers or the sum that will be produced through this 11:2 compressor or 4:2 compressor. Okay. So, if I just see the corresponding architecture, that means the inside of this 11:2 compressor. So, at that time you see that the cells are like VLSI that is coming like this. Okay. So, here initially what is there, that means I have at this very first level, if this is the that means level 0. So, then 3 full adder cell I have used where it is consuming total 9 number of inputs and it produced what 3 number of carries and 3 number of sums. So, in the next level, so in the previous case what I says level I carry that enters into level I plus 1 number 1, that means level. So, here whatever that sum I am getting from this, I have used 2 full adder cell, one sum I have used here and one sum I have used in this full adder cell and I have produced how many carry? So, total 3 carry. So, 2 carry comes for this particular full adder cell, 1 carry comes at this particular case. Okay. So, then again at level 1 I am producing 2 output carry and 2 sum. Then again that 2 sum again enter into 2 full adder cell, okay, and the 2 carry are basically coming to the 2 carries are coming to the corresponding 2 full adder cell. Then another of this sum is already left. So, that is coming to this full adder cell and another position to this full adder cell is already that means left. So, another of the input which is coming over here and in this particular case also another input is coming over here. So, that means at level 2 Okay. At level 2 again I am doing using 2 full adder cell, I am producing 2 carries and 2 sum. Okay. So, then this sum is basically coming over here and 2 carry from the previous level. So, those 2 carries are coming in this stage. Okay. So, then again this sum is coming, and the carry from this particular full adder that are coming over here, okay, and I am getting final sum and final carry at this particular adder tree. So, this structure is very much regular. I have not used any like here full adder, then half adder, then carry propagate, that is at the very final level I have to use this carry propagate adder, that is a different issue. But unlike this Wallace tree and adder tree method, so if I use this for each of this position, so if I use this kind of structure or this compression method, so this is giving me one very much regular structure, which is very much useful in VLSI architecture. Okay. So, for that means 4:2 reduction method, so it will at the very first it will consider one carry save adder tree, that means one carry save adder level, then again that sum and carry along with the another carry that will produce 2 output. Okay. So, now for 16 I will use this 4 of them, then again 4 will be generated from this, then again that will be. So, using this 3 level now I can add 16 number of multiples using this 4:2 compression, and you see this structure is very much regular in nature. Okay. So, that is why this tree multiplier with a more regular structure based on this 4:2 this reduction modules. Okay. And due to its recursive structure, a binary tree is more regular than a 3:2 reduction tree when laid out in VLSI. So, whatever we are doing in that means in Wallace tree and adder tree, that are either 2:2 or 3:2, that means this carry save adder we are using. So, 3:2 means we are consuming 3 and we are producing 2 outputs, basically that is the full adder cell, and in half adder cell that is 2:2 means 2 input it is taking and 2 output it is producing. But here what we are doing, we are using inside of that we are using 3, but whenever we are considering the multiples, so at that time combination of 4 we are considering, and this gives me a regular structure. Okay. So, this is that means the layout of the corresponding partial product reduction tree composed by this 4:2 reduction module. Okay. So, as I said that this gives me a better that means or a regular structure while we are implementing it in VLSI. Okay. So, after that what I have to use, what I left the third, which is redundant to binary converter. So, I can use any of the first adder which are any of this adder, that means which will be this any of this adder, whether that will be carry select adder or carry look add adder or carry propagate adder or conditional sum adder, any of this adder for the final 4 bit or 6 bit or 8 bit addition operation, while this terms comes to 2. So, at that time, that means after tree reduction the final terms will come whenever that will reduce, that will come to the 2. So, at that time you have to use any of this first adder to get the better result or to reduce the delay for that particular multiplier design what you are intended to do. Okay. So, this is the, that means in Wallace tree the number of levels you can get by log of this. Okay. So, this I think we have already discussed. So, this is the using carry ripple adder also you can do. So, we have used mostly we have used what for carry save adder, and we use carry propagate adder while we are considering this tree reduction method, but ripple carry adder also you can use. But if you use ripple carry adder, so at that time you will get the delay will be more. Okay. So, that means to reduce or to improve the corresponding delay or that means the speed of operation. So, that is why we have to use this carry save adder, or you have to use this carry propagate adder. So, this is the comparison tables of all the multipliers we have discussed till now. So, we have used, or we have that means seen array multiplier, we have seen this Booth multiplier, we have seen this Wallace tree multiplier, or else we can use this hybrid of this, that means Booth's algorithm and then Wallace tree multiplier, and we have seen this serial parallel multiplier, and this is behavioral multiplier, means that nothing but the generic multiplier architecture, that is nothing that shift and add based multiplier. And this is basically the FPGA implementation, and along with that it shows that in serial parallel it consumes the more, that means the lesser area in compared to all the architecture. Okay. That means we are generating the in a serial fashion we are using. So, that is why the time requirement, the completion time requirement is also more if you see this table for that particular case. Then the next is that the Wallace, that means the modified Booth and Wallace tree multiplier, that means requires 2672, and the Booth multiplier requires 2649. Okay. Whereas, that means the lowest possible, that means if I consider this parallel architecture, this gives me the lowest possible the number of area requirement, but here the delay requirement is 24.43, but the delay requirement for this is 18.53. Here what we are doing, in Booth multiplier the area requirement is lesser. In Wallace tree, this is the first addition operation, that means the delay is reduced in compared to the Booths. So, while we are hybriding these two architecture, that means I will get the benefit of area as well as I will get the benefit of delay, which I am getting in case of hybrid multiplier, which is Booths plus Wallace tree. So, 2672 just minimal increase from this 2649 number, and here 18.93 and here it is 18.53, that means just a minimal increase in the delay too. So, that means I am getting one optimized circuit if I use hybrid architecture in this case. So, rest of the delay power, that means area power, the power wise this circuit is also very good in compared to this. Time requirement is much more higher on this, and behavior multiplier it all, that means consumes also a that means very large number of area as well as power as well as delay. Okay. So, in that means overall overview, if I say that area wise this modified Booth and Wallace multiplier that is small, okay, and delay wise this is the fastest, power consumption wise the smallest is the parallel pipe, but as delay is very much higher, that means higher side. So, this is the on the power side also we are getting much more savings in this hybrid architecture. So, that means till now we have seen this unsigned multiplication. So, this is the, that means this end of the unsigned multiplication. From the next class onwards we will sign multiplication techniques. It is this is not the end of this unsigned multiplication architectures. As I said that there are different several research, that means literatures are available on the net internet, or that is available in the Google or IEEE or any other scientific sites. Okay. So, if you are interested to design one, that means if you are focusing on to design one high performance multiplier architecture, then please follow those literatures. Okay. And you can also discuss via a discussion forum. So, thank you for today's class.